Hello everybody, welcome into another lesson. So today is just going to be an introduction to matrices. And we're going to talk about what a matrix is. So if we're talking about one matrix, that's the singular term as a matrix. If we're talking about more than one matrix, or in general, we would say matrices. That's the plural form. So what is a matrix? A matrix is a rectangular array of numbers. That's just simply the best way to think of it. So a matrix can be classified by its rows times its columns. So here you have some arbitrary matrix with entries A, B, C, and D. Now these will usually have numbers. I'm just trying to represent the matrix itself, but the rows are horizontal. We classify that by M. Columns are vertical by N. How can you remember rows by columns? Well, rows go straight across. They're horizontal. Think of it like rowing your boat across the river. Usually you're going to go horizontally, straight across. A column's vertical. So think of it like you're in a nice building that has pillars in it. Those are columns. They stand straight up. That's probably the best way to remember rows and columns. We classify a matrix by the number of rows times the number of columns, M by N. In this case, this particular matrix has 2 rows and 2 columns. This is a 2 by 2 matrix. And a square matrix has the exact same number of rows as it does columns. Other examples of square matrices, you have a 3 by 3 here with entries A, B, C, D, E, F, G, H, and I. It has 3 rows and 3 columns. And then you just have a matrix with entry A in it. It's got 1 row and 1 column. That'd be a 1 by 1 matrix. These are all square matrices. Of course, not every matrix is square, as we're going to see, but that's some of the first basics of it. So let's go ahead and get into classifying some matrices. So I just have a matrix with 2 entries, 7 and 0. So again, we always classify a matrix by the number of rows times the number of columns. So this matrix has entry 7, 0. How many rows does it have? It has 1 row, so it's just 1 row straight across, so it'll be 1 by how many columns? It has 2 columns, so this is actually a 1 by 2 matrix. It's definitely not a square matrix, but this is a 1 by 2 matrix. Alright, let's say I have a matrix with entries 6, -3, 10, and 8. So I have a matrix here with entries 6, -3, 10, and 8. How would I classify this? First, how many rows are there? You got just 1 row straight across by how many columns? 1, 2, 3, 4 columns. So this particular matrix is a 1 by 4 matrix. Alright, now you have a matrix with entries 4, 32, and 3. So this time the entries are arranged vertically, but you have entries 4, 32, and 3. Again, we're going to go first by number of rows. How many rows are there that go straight across from left to right? 1, 2, 3. This matrix has 3 rows by how many columns? Well, everything's arranged in 1 single column going up to down, so this would be considered a 3 by 1 matrix. Alright, now, what if I gave you something like this? -3, 7, 15, 0, 0, 0, 3, 3, 1, 1, 6, 7. So we have a lot of entries in this matrix. You have -3, 7, 15, 0, 0, 0, 3, 3, 1, 1, 6, 7 in this matrix. Again, first, how many rows does this have? Straight across from left to right, 1, 2, 3 rows. By how many columns? That go straight up and down. 1, 2, 3, 4. This would actually be a 3 by 4 matrix. It has 3 rows and 4 columns. Alright, let's see. We have 33, 45, -9, and 20. So we have a matrix with entries 33, 45, -9, and 20. How many rows does this have? 2 rows straight across, so you have 2 rows, and then you also have 2 columns. So this is a 2 by 2 matrix, and since the number of rows is the same as the number of columns, this is actually a square matrix. Since the number of rows is the same as the number of columns, this would be considered a square matrix. One more for classifying, and then we're going to talk about augmented matrices. So we have 3, -1, and 4. 6, 0, and -5. So we have a matrix with entries 3, -1, 4, 6, 0, -5. How many rows? We got 2 rows going straight across. By how many columns that go up and down? You have 3 columns. So this particular matrix would be considered a 2 by 3 matrix. So again, you classify a matrix by the number of rows times the number of columns. And that would be the order of your matrix. Alright, so that's classifying matrices by their order. Now, you're probably wondering, okay, that's great about matrices, but why the heck would we ever need to use them? Well, we can solve systems of equations using matrices. We're not actually going to solve any systems today, but we're going to set them up. So, let's say, for example, you have 6x minus 7y equals 11, and then you have -2x plus 5y equals 1. So far we've learned about substitution and elimination without using matrices. Now we're about to cross over and use matrices to solve systems. So what you're going to do first is you're going to ignore the right-hand side of the equal sign. Go ahead, set up what's called your coefficient matrix. So you're going to have 2 rows by 2 columns to start. So the first number in the first row is the coefficient on your x. That would be your 6. In fact, we could call this your x column. In the second row, you'll have a -2 for your first number, right? Because that's in your x column. And then your second number in the first row of the matrix would be the coefficient on your y, which would be -7. So here's your y column. And then the second number in the second row is going to be the coefficient on your y, which would be 5. So far you've set up your coefficients, but now this is where we get into dealing with it to the right of the equal sign. What you're going to do is put a dotted line, that'll denote the equal sign, and then in each of the rows you'll put what's to the right of the equal sign. So to the right of 6, negative 7 is that 11, to the right of negative 2, 5 is 1. Whenever you see a matrix with this dotted line, this is what's called an augmented matrix. This is called an augmented matrix. So this augmentation line functions the exact same as an equal sign, but I'm going to erase this x and y now since I think we get what it is, but that is how you would represent a system of equations in matrix form. And I got more of that. So I have 7x plus 4y equals 22. And then I have 5x minus 9y equals 15. So I have the system 7x plus 4y equals 22, 5x minus 9y equals 15. How can I represent this as an augmented matrix? So first, set up your brackets. Now the first entry in your first row will be the coefficient on the x of the first equation. That's going to be 7. The second entry in the first row will be the coefficient on your y in the first equation. That'd be 4. And then we can do an augmentation line to denote the equal sign, and to the right of that equal sign is a 22. That would belong in the first row. Alright, time to go on to the second row. So the first number in the second row is the coefficient on your x. That'll be a 5. The second number in the second row is the coefficient on the y in the second equation. That'd be negative 9. And then to the right of that augmentation line would be that 15. So that is how you would represent this particular system in matrix form. Alright, let's change it a bit. So we have x plus 10y minus 2z equals 2. We have 5x minus 3y plus 4z equals 0. And then we have 2x plus y equals 6. So now you have a 3-variable system. You have x plus 10y minus 2z equals 2, 5x minus 3y plus 4z equals 0, 2x plus y equals 6. Alright, so how can we represent this in matrix form? So go ahead, set up your brackets. So the first number in the first row is the coefficient on the x in your first equation. That's just going to be 1. Then the coefficient on your y in the first equation, that's going to be 10. Then the coefficient on your z in the first equation, that would be negative 2. And then you can set up your augmentation line. To the right of the equal sign is 2. Now let's start the second row. So the first number is the coefficient on the x in the second equation. That'd be 5. And then the next number is the coefficient on the y. That'd be negative 3. Then the next number is the coefficient on the z. That's going to be 4. And then to the right of that augmentation line is that 0. And then we're going to have a third row because this is a 3-variable system. So the first entry in the third row, coefficient on the x is positive 2, coefficient on the y is positive 1. Okay, let's look at this third equation. You don't see a z entry at all. When you're converting this to matrix form, you still have to account for z. What would actually be the coefficient of z? It would just be 0, right? So we'll put a 0 in for that z, and then now we'll, to the right of that augmentation line, we'll put that 6. So every variable is accounted for in every row. We just happen to have a 0 for the z in the third row. But that is how you would convert this system into an augmented matrix. Alright, one more, and then we're going to go on to working backwards. So you have x minus 3y plus z equals 1. You have 4y equals 0. Then you have 7z equals negative 5. Alright, so how are we going to represent this matrix? Well, we're going to do it like we would any other one. So let's set up our brackets. So the first entry in the first row, coefficient on the x, that's a 1. Coefficient on the y is negative 3. Coefficient on z is positive 1. And then we can do an augmentation line, which would make, to the right of that would be a 1. Now the first entry in the second row will be our coefficient on the x in the second equation. In this case, that's going to be a 0. Then the coefficient on y is positive 4. Coefficient on z is also 0. And then to the right of the equal sign is to the right of the line of augmentation. You'd put the 0 there. Alright, first entry of the third row's coefficient on the x, that's also 0. Then the second entry, coefficient of the y, is also 0. Then the coefficient of z is 7. And then to the right of the augmentation line would be that negative 5. So that's how you would represent this particular system as an augmented matrix. Alright, now we're going to do a few exercises where we work backwards. We're going to be given an augmented matrix and we have to write out the system from it. So let's go ahead and do that. So the first augmented matrix, you have 3, 4, and 9. Then you have 1, negative 1, and 3. So how can we represent this matrix as a system? So take this one row at a time. The first entry of your first row is always going to be the coefficient of your x variable. So you would have 3x, and then the coefficient of your y variable is the second entry in the first row, so that'd be plus 4y. And then remember that augmentation line functions as an equal sign, so you would say 3x plus 4y equals 9. Now we have a second row. So the first entry of the second row is the coefficient on your x variable. That's just positive 1. That'd just be x. Second entry of the second row is coefficient on the y. That's negative 1. So you'll have x minus y. And then to the right of that augmentation line, you could say this equals 3. So this matrix signifies the system 3x plus 4y equals 9 and x minus y equals 3. And I got more of these. Alright, we have 7, negative 5, and 0. Then we have 8, 3, and negative 2. So how are we going to represent this particular augmented matrix as a system of equations? Well, again, the first entry of your first row is the coefficient of your x variable. So that is going to end up being 7x. And then the coefficient of your y variable is the second entry of the first row. That's going to be then minus 5y equals, because that augmentation line again functions as an equal sign, so you could say 7x minus 5y equals 0. Now we have a second row. First entry is the coefficient on your x. That's going to be 8x. And then the coefficient on your y, so that's plus 3y equals negative 2. So that's how you could turn this augmented matrix into a standard system of equations. I got just 2 more, then we're actually done with the lesson. All right. 9, 12, 3. Then our augmentation line, 0. I know 10 goes here. Now let me see what comes to the left of it. Negative 2, 18, and 5. And then 1, 7, negative 8, and negative 4. Alright, so you have, this time you have a 3-variable matrix. We have an augmented matrix where we have 3 variables. So how can we represent this as a system of equations? So the first entry in the first row, again, is the coefficient of your x variable. That's going to be 9x. Second entry of the first row is the coefficient on your y variable, so that'd be plus 12y. And then the third entry of the first row is going to be the coefficient of your z variable, so that'd be plus 3z. Augmentation line is equals that 0. And then the first entry of the second row is the coefficient on the x, that'd be negative 2x. Second entry is the coefficient on your y, so that'd be plus 18y. Third entry is coefficient on z, so that'd be plus 5z. Augmentation means equals that 10. And then we have one more row. Coefficient on x is just 1, so that'd be x. Coefficient on y is 7, so that'd be plus 7y. Coefficient on z is negative 8, so minus 8z equals negative 4. So you were able to convert this augmented matrix into a 3-variable linear equation system of 9x plus 12y plus 3z equals 0, negative 2x plus 18y plus 5z equals 10, and x plus 7y minus 8z equals negative 4. I got just one more and then we are done. This is a good one. Actually, that should be a negative 5. But I'm pretty sure this one's negative 25. Alright, and then negative 1, 0, 7, 3, 7, 4, negative 1, negative 10, 6, 23, 0, 8, 1, negative 11, negative 21. So we have a 4 by 4 augmented matrix. Augmentation does not change the order of what's to the left of the augmentation sign, by the way. I should specify that. So if you ignore what's to the right of the augmented line, you would have a 4 row by 4 column matrix. This would be a 4 by 4 square matrix. But how are we going to turn this into a system of equations? So normally it's x, y, z, but we go in alphabetical order. It's convention to make a 4 variable linear equation system. Your first variable would actually be w, then x, then y, then z. So in the first row, first entry of the first row, that's the coefficient on my w variable, so that would be 6w. And then the second number is my coefficient on the x variable, which would be plus 2x. And then the coefficient on the y, which is negative 1, so minus y. Coefficient on z, so that's minus 5z, equals negative 25. And then you have, in the first entry of the second row, coefficient on the w, which is negative 1, so this would be negative w. And then coefficient on x is 0. We don't have to write that for the system. The only time you got to account for 0 is in a matrix. When you're writing out the system, you don't have to do that. And then we're going to go right to the y variable, which would be plus 7y. And then the z variable, so that's plus 3z, equals 7. Third row, first entry is my w variable coefficient. That would be 4w. Coefficient on x, that'd be minus x. And then coefficient on y, that'd be minus 10y plus 6z equals 23. And then the final row, coefficient on w is 0. We don't even have to write a w there. But coefficient on y, coefficient on x, that's positive 8x. Coefficient on y, that's positive 1, so plus y minus 11z equals negative 21. So here is your 4 variable linear equation system based on this augmented matrix by taking all the coefficients and everything to the right of the line of augmentation. You get 6w plus 2x minus y minus 5z equals negative 25. Negative w plus 7y plus 3z equals 7. 4w minus x minus 10y plus 6z equals 23. 8x plus y minus 11z equals negative 21. So that's how you work backwards and get a system from this. Now, there are many methods for using matrices to solve systems of equations. In the next lesson, we're going to talk about something called Gauss-Jordan elimination with back substitution, which will introduce something called row echelon form. Just plain row echelon form. Reduced row echelon form will be the lesson after that, but we're going to use Gauss-Jordan elimination with back substitution in the next lesson using matrices. And I should tell you, good news for everyone. We were only writing out the system. I'm not going to ask us in this course to do anything above a 3 by 3 as far as solving a system, because it just gets to be too much. Now, if you go on to take a future course called linear algebra, which comes after calculus 3, you may need to solve 4 by 4 and greater systems, but usually you'll have a graphing calculator to do just that. Because you can actually use graphing calculators to solve matrices also, but my goal is to teach you how to do it by hand and algebraically here in Precalc. So that's it for this lesson. I will see you all in the next one. Have a great day.